In this video, we're going to talk about how changing the temperature of a solution affects the pH. So in the last couple videos, I've been saying a lot about at 25 degrees, at 25 degrees, at 25 degrees, that you are all used to the idea of pH 7 being neutral. That is only true at 25 degrees. We used the kW for 25 degrees. 25 is considered standard room temperature in science, is why it gets referenced a lot. But clearly we often work at other temperatures that we may heat a solution up on a hot plate or cool it down in a freezer, depending on what it is that we need to do. So as the temperature changes, none of these relationships change mathematically. What does change is the value of kW. So just like any other equilibrium constant, the value of kW changes as the temperature changes. Which means that our relationship between hydronium and hydroxide mathematically stays the same, but the product of these concentrations is always equal to a constant, but that constant has changed. So I've mentioned that the temperature changes what neutral pH actually is, and we now have the tools to actually prove that. So let's calculate the pH of water, of pure water at 65 degrees Celsius. At 65 degrees Celsius, kW is 1 times 10 to the minus 13th. So we can see that our value of K has increased by 1 order of magnitude by increasing the temperature from 25 to 65. So if we want to calculate the pH of water, first off, water by itself is neutral. Water is capable of acting as either an acid or a base, but if you just have water by itself with nothing else in it, it is neutral. So we're essentially being asked to calculate what is the pH of neutral at 65 degrees Celsius here. So if we remember that neutral means not anything about the pH, but that the hydronium ion concentration is equal to the hydroxide ion concentration. This was our definition of what it truly means for a solution to be neutral. That, combined with this relationship, is all we need to be able to ultimately calculate our pH. So we know that kW is always equal to the hydronium concentration times the hydroxide concentration. We have a value for kW of 1 times 10 to the minus 13th at this temperature. So we can plug that in. And since we know we're looking for the pH of water, we know we're looking for the pH of neutral. If these two concentrations are equal, we can plug in one for the other. So let's say we replace the hydroxide concentration with the hydronium concentration. They're mathematically equal to one another when the solution is neutral, so we can do that. So that means that kW is just equal to the hydronium concentration squared. So if we sorry, just spotted a mistake in my own answer key, but it's fine. If we take the square root of both sides, we find that the hydronium concentration is going to be equal to 1 times 10 to the negative 6.5. I'm actually not going to put that in my calculator because it's going to be easier to find my pH if I don't. My pH is then going to be the negative log of the hydronium concentration, which is 10 to the minus 6.5, which is a pH of 6.5. So at 65 degrees Celsius, a pH of 6.5 is neutral. So we're used to thinking of 7 as neutral, but that's only true at room temperature. It is not true if we're at anything other than 25 degrees Celsius. You'll see it's not a huge change in the pH, just half a pH unit, but that's not nothing. And it is something to recognize that if you had a solution that was, say, pH 6.8, if you've got that 7 stuck in your head, you might think it's slightly acidic because it's a little bit below 7, but at 65 degrees Celsius, that pH is above neutral, which means that it is actually a very slightly basic solution. So in some cases, it can be important to recognize this.